571. Okay, Michael Chow was here to give the last lecture. I wonder if you have any questions regarding the last lecture. Okay, this is the book we use. I believe it's available in the bookstore. And also, I also would lecture from Hoffney and called the principle of planar optics. And you'll find many interesting topics in nano optics in that book. I asked for a reserved copy to be put in the library. I believe you can also buy this book from Amazon.com if you're interested. But I will provide you with the lecture notes as well as I do lecture from that textbook. Okay, that's the best I could do. Today I'd like to talk about chapter 2. If you don't have anything else regarding chapter 1, I'd like to talk about chapter 2 of my book on waves in layered media. Okay, so what you learn from chapter 1 is that many of the principles and boundary conditions and so on actually embedded in the vector wave equation. There are two vector wave equations. One is this one over here. Say if I assume that there's no source, this is the vector wave equation, and you have the other one for the magnetic field. And if there's some source, this would be something like I omega mu j, and this would be something like minus I omega epsilon m or something like that. Okay? And you can prove that the boundary conditions are embedded inside the vector wave equation. You can also prove that the reciprocity principles are also in the vector wave equation. Also, you can derive uniqueness principle from the vector wave equation. And what it says is that we don't actually have to work with Maxwell's equations. If omega is not 0, you can actually start to work with the vector wave equation. It has all the properties of electrodynamics. Only these equations have problem when omega is equal to 0. Okay, why do they have problems when omega equals to 0? You know why? What is the issue with this equation if you set omega equal to 0?
Because they will have to solve all four Maxwell's equations. If omega is high, then the immediate is not just the first.
Yeah, but I know you got the point. But why is this equation in trouble when you set omega equal to 0?
Oh, because it lies in the null space of.
What is that?
The solution is in the null space. Because the second term on the left-hand side and the right-hand side is 0.
Yeah, you got the right point. Okay, when you set omega going to be 0, you have an equation that looks something like this. And this vanishes a lot faster than this one. Okay, so this equation to the leading order approximation will be this. And does this equation have a solution? Equation such as this curl of A is equal to S has no solution. Why is that so? Why is this equation not having a solution? Yes, sure. That's right. There's one thing is that the curl of A does not define uniquely what A is. We learned this in undergrad. You have to define both the divergence of A as well as the curl of A, because otherwise A would be undefined. Another way to say this is that this equation has a null space, that I can always add the gradient of something to this equation and it remains unchanged. The curl of the gradient is equal to 0. And another way of saying this is very much the same as a matrix equation. M dot x equals to b. And if this matrix M has a null space, which means that there exists a vector x of n such that this is true. Okay, if there exists such a vector x of n that this is true, then this equation has no unique solution, because I can always add a null space solution of arbitrary amplitude to this thing, and it will still always satisfy the same equation. So you can look at this from linear algebra or vector wave equation viewpoint. Okay? So as long as omega is not equal to 0, these equations are same, and they are reasonable to solve. So let's try to solve this equation for the layered medium. That is that if we have layering such as this one over here, this is z, and then mu is a function of z, epsilon is a function of z. So this might be epsilon 1 mu 1, epsilon 2 mu 2, epsilon 3 mu 3, and so on. This might be epsilon n mu n. And how do we solve this problem? And we can assume for simplicity that the electric field is pointing only in the y direction. Okay, let's say that this is x and this is y. Okay, that we only have an electric field pointing in the y direction. And if you look at the vector wave equation, that if this is the case, then you can already say something for sure, that if E points in the y direction, that this has to be true for a source-free medium. Okay, we assume that there's no charge in this system, that once the wave propagates through this medium, there's no source. Okay, and this equation tells you that partial z epsilon Ez plus partial x ex plus partial y ey equal to 0. But I only have y component in this equation. Okay, so this must be 0 because I assume that only y component exists. I immediately conclude that partial y ey is equal to 0. So if such a kind of solution exists, and it is y polarized, then if the solution is y polarized, then there has to be no variation in the field. Okay, the y variation in the field has to be 0. And so if you look at this equation, then you can actually simplify. You can actually simplify that equation to arrive at something that is somewhat simpler than that one, because then you have mu curl of mu inverse curl of Ey. Ey is only pointing in the y direction, minus omega squared mu epsilon Ey. Let's assume there's no source in this problem, because I'm just interested in studying a plane wave propagating through this medium. So I'm only interested in plane wave. Okay. And because there's no y variation, so this must be something like partial x cross of ey. Okay, partial y is equal to 0. And then there should be a partial of z as well, cross of ey. Okay, if I look at this term, this will have two terms there. Okay, then x cross y gives me z. Then if I just look at this term alone, then we get z, x cross y, z, give me partial x, ey. Okay, and then partial z, z cross y gives me minus x, so it gives me x partial z of ey. So that gives me two terms. And then if I look at the next term that comes about, it will be x partial x plus z partial z, because I assume no y variation already. Okay, this is true, so I don't have to include the other term. Mu is a function of z in this problem. Mu is a function of z, and if I plug in these two terms, which is minus x partial z ey plus z partial x ey. If I plug that in, then I can figure things out. X cross x gives me 0. X cross z gives me minus y. So minus y partial x squared ey. There's a mu inverse here. Mu inverse doesn't matter. I can put this mu inverse outside because it does not depend on x. Okay, then x cross, then I have z cross x. Z cross x gives me, what does z cross x give me? Z cross x gives me y, right? There's a minus y. But then I have to worry about this. Partial z, mu inverse partial z ey. That's what the second term gives me. Why is that I cannot take this mu outside, whereas I can take this mu outside here? I have to leave this mu inside. What is the reason for that? Aditya, what do you think?
It's a function of z.
So?
So,
So
you can't take it out, right? Because
how would you say it mathematically?
then you'll have to do a chain rule.
What?
You'll have to do a chain rule.
Okay. You can say it mathematically in a different way, but let me just conclude by saying that z cross z term is 0. So what is remain of the first term is just these two terms. And then what is left of the last term will be just omega squared mu epsilon y hat ey is equal to 0. But you asked me a question yesterday, which I thought you could have answered using a different mathematical notion. That if you have this curve cross curve of E, it can be written as gradient of divergence of E minus Laplacian of E, right? We know this notation from our undergraduate days. And this is usually 0 in free space. And hence this can be written as a gradient divergence of the gradient of E. Okay? And in short, we often write this as this. Okay, I think the question I asked in the homework was, why is that only in Cartesian coordinates can you say that this is equal to that? But you cannot say that this is the case in, say, cylindrical coordinate system. Neither can you say this in spherical coordinate system. Why is this untrue for the later case, but this is true? What is the mathematical reason for it?
Because the basis vectors are position dependent.
Right? These are position dependent, right? Rho hat, phi hat, z hat is constant, but phi hat, theta hat, r hat are position dependent. Depending on where you are in space, they point in different direction. So, mathematical way of saying this, that this thing and this thing do not commute. In other words, mathematically, we always write it as this manner. They do not commute. This is a mathematical notation that says that A, B is equal to A, B minus B, A. Okay, A commutation B is equal to that, and if that is equal to 0, then it means that these two are equal, and we say that A and B are commuting if this is 0, and this is the notion that the Laplacian operator and the rho hat function do not commute. Okay, and that's what I want you to say. And so, another way of saying this is we cannot take this outside because these two things do not commute. As a mathematical notion. Okay, so the summary of the story is that given something like that, the equation we need to simplify and solve in a layered medium is not the full vector wave equation, but a scalar wave equation of this nature, partial squared, partial x squared, plus partial z. I have to put in my new inverse somewhere. Okay. Mu inverse partial z. I can put mu somewhere here as well. Plus omega squared mu epsilon. Yeah, there should be a mu somewhere. I should multiply this 2 by mu somewhere over there. Then that makes the equation balance up. Ey equal to 0. So the short end of the story is that the solving of this complicated problem for a planarly layered medium, assuming that I have a wave polarized in the y direction, reduces to solving a simpler equation, which is a scalar wave equation. So this is a scalar wave equation, and it's also called a PDE. The PDE stands for a partial differential equation. Okay, so we need to solve only a scalar PDE.
There should be no mu for the PDX.
There should be no mu here, right? Because it cancels this. It cancels this one. Oh. Okay, yeah. Thank you for pointing that out. So this is the scalar wave equation and the PDE to be solved. Okay. So this is a wave which is called a TE polarized wave. Because I'm studying a wave that will propagate through this medium in this direction. And the electric field is polarized in the y direction. And hence, this is the wrong picture actually. I can draw this picture like this. The electric field is polarized in the y direction. So I should draw something like, if this is the x direction, this is the z direction, if y is propagating into the paper, then the wave is propagating something like that. There's no y variation in this picture, so I cannot draw this picture like that. Because that picture will have entailed y variation. So the wave might get multiply reflected. And for a TE polarized wave, I have this mental picture of how the wave propagates through this medium. Okay? But it turns out that the TE polarization is very special. It seems that for TE polarization, Ex is not equal to 0, Ey is not equal to 0, Okay. EZ equal to 0. Those are the possibilities. Whenever you have a wave where the electric field is completely transverse to the z direction, we call that the TE polarization. For the TM polarization, you can go through the same analysis and arrive at the fact that Hx must not be 0, Hy must not be 0, Hz equal to 0. And by the same token, you can go through the same analysis, start with the vector wave equation for the magnetic field, and arrive at an equation that looks very similar to this, which of course you can also derive using duality principle. You could also have arrived at such an equation for Tn polarization. Okay. So those are not the only way to study TE and Tm polarization. These are the two possible equations, one for TE, one for Tm. But there are other ways to study TE and Tm polarization. You can also say that whenever I have a TE wave, it is characterized by the fact that Hz is not equal to 0. Whenever I have a Tm wave, it's characterized by the fact that Ez is not equal to 0. Okay? TE wave has Ez equal to 0, but Tm wave always has Ez not equal to 0. E wave always has Hz not equal to 0. We can do a simple plane wave example to understand why. Say if I look at this picture again, if the electric field is pointing into the blackboard, okay, E is to the y, Ey, then the wave is propagating in that direction. Then the magnetic field, H, must be pointing something like that as it propagates. And you can clearly see that for this TE polarization, Hz is not equal to 0. And you can go through the same exercise for Tm. For Tm wave, H, say, is pointing into the blackboard, then E must be pointing something like that. E actually has to, H has to actually point out of the blackboard, so that E cross H is in the direction of propagation. And then you can see that Ez is not equal to 0 for Tm. So Te, Hz not equal to 0, Tm, Ez not equal to 0. So one way to characterize Te and Tm waves is to use the fact that their z components are not 0. So can we derive other forms of equation for Te and Tm waves? We can, and let's see how we can do that for the case of, say, the TE polarization. So we start with the vector wave equation for magnetic field, which looks something like this. So this is the vector wave equation for H. Does everybody agree? Okay? Let's see from this equation if we can derive an equation that involves Hz only. Okay, let's see if that's possible. And the normal way of doing this, or this is one of the ways of doing this, is to write my del in terms of the transverse component plus the z component. Transverse here means that I keep only this component transverse to the z-axis. So I can break my del into these two components. I can also break my h into a transverse component plus a longitudinal component. Okay? So my del cross h would have 4 terms. If I multiply this out, it will have this term crossing with this term, okay, and then it will have 4 terms. then if you multiply all these four terms out, it would be something like this. And there's no last term. Why is the last term not there? Right, the RC cross HZ equal to 0, because anything pointing in the Z direction gives 0. So, if I were to look at this, then what direction is this pointing? Can you? Z, right? This is pointing in the Z hat direction. This must be pointing in the transverse direction. Anything in the Z direction crossing with anything in the transverse direction must be pointing in the transverse direction. So this must be pointing in the transverse direction. So if we do the next step over, which is to break this into this one over here, I would have plus this cross HS plus LS cross HZ. Okay, plus this one. Okay, and then so what I have done is that if I work this out, I'm only interested in the Z component of this equation. I want to extract the Z component so that it is an equation that involves HZ. So if you look at this, this is pointing in the Z direction. Crossing with this would never give me anything in the Z direction. So I can throw this thing out. But these are the transverse direction component. This transverse component crossing with this component will give me Z direction. This one will do the same. And then the others will give me transverse component. So the only thing that will give me Z direction only is that I would have these two terms left. This is my first term, and then I would have this term left. Okay, those will give me terms that are pointing in the Z direction. Z directed. Okay, Z directed terms. And then let's try to simplify these two terms then. Let's try to simplify the first term. The first term that we have is this term over here. Cross HS. But these two commute. I'm using the same mathematical notion as I just taught you a little while ago. These two commute. So you can take this outside. Okay. So I can write this in this manner. Everybody agrees this is a function of Z only. This is partial X and partial Y. So they commute and they can take them outside. And then I have to use a mathematical identity to simplify this. And I hope that all of you would remember this mathematical identity, that this is A cross B cross C is the back of the cat formula, A dot C minus C A dot B. This is called the back of the cat formula. Okay? So this can also be applied to this, but you apply this to this with caution, because these are vectors. But when you apply them to operators, you better be mindful of the order of the operator. They always operate on something to the right. And you make sure that when you write them in this form, you do not violate the fact that these are operators. So if I apply this to this, then I would have something like something like this for the first term, right? This operates on this, and this has to be 0 because both of them are 0. Cannot be. What? Did I get both of them in 0? This is 0, this is 0. So this term does not contribute. Did I do anything wrong here? Because
That is HS.
what is that?
The second line is HS, not HZ.
HS, right? Sorry. This is sorry. Thanks for pointing that out. Okay, so it would be bizarre if both of them are 0. Then I cannot derive the equation that I want to arrive at. So this is only one of them is 0. So, but what is this equal to? Well, I know that B has to be 0 for this problem. From this I can gather that mu plus, again, the partial z does not commute. Okay, this is true, but I can let the mu be outside, but the mu over here cannot be taken outside. So I conclude the fact that the transverse divergence of HS is mu inverse partial z mu hz. Okay, so I can replace this term with, here I replace it with this explicit form, and then this one I replace it with this one over here. Okay, so at least this first term can be simplified as such. What about the second term? The second term is a lot easier to simplify. Second term is a lot easier to simplify. Because of what? Because this epsilon inverse commute with this del, right? I can take it outside. So the second term can be written as epsilon inverse cross of hz, right? And then I use the back of the cap formula again. This is just equal to minus okay, the second term, and this again is equal to 0. So this is just minus the transverse Laplacian of hz z hat. And so the second term is just that. And then if I gather all these terms together, I have simplified the first term into that. If I gather this together with that, I end up with an equation that looks something like this. Plus this term, mu inverse partial z mu, and then plus omega square mu h z is equal to 0. collecting this term and plus the two terms I had before. Okay, so this is the equation that I have. Doesn't look right, does it? I should multiply this by see, I'm dropping this epsilon inverse over here. And finally, I should have an epsilon inverse somewhere. Okay, so this should be epsilon inverse over here. And so there should be an epsilon inverse over here. If I put a parenthesis over here, there should be an epsilon inverse over here, epsilon inverse over here. Okay, because then there should be an epsilon inverse over here. So this is the final equation that I have, and I can rewrite it as
Minus sign.
there is a minus sign.
The number S dot H S equals
Second from the bottom.
Second from the bottom.
There should be a minus sign, right? There should be a minus sign here. There should be a minus sign. And if I have a minus sign there, then that would make things